Now, I've given a lot of talks where I've talked about, used metaphors of eggs and biorobots and computers and all that kind of stuff to try to explain mRNA vaccines and the genetic vaccine technology. This time, because I'm speaking for CME units and I'm speaking to a highly educated audience, I'm going to go a little more technical, so forgive me for that. Okay? So here we go. Next slide. So just to remind, waiting for the next slide, showing my bald spot. Okay, the slides are up. Next slide, please. Central dogma of biology. We got to start there, just so we have common ground. DNA makes RNA. DNA makes RNA, and that makes protein. mRNA makes protein. There's a lot of kind of intimidation, fear, consternation about what is mRNA. It seems very spooky and foreign. mRNA merely means messenger RNA. That's the form of RNA that is used by the protein translation machinery. What is that protein translational machinery? I'm going to go through this quick. It'll be painful, and then it'll be over. The protein translation machinery is the ribosome. Next slide. Sorry. I'm forgetting that I'm not controlling the slides. Okay, so the ribosome is when I talk in the podcasts about the little molecular robot in our cells, it's a whole bunch of these things called ribosomes. And ribosomes have different parts, components to them. And in fact, they're involved in all three main forms of RNA. So messenger RNA is only one of those forms. The transfer RNAs that carry the amino acids for polymerizing proteins is another form of RNA, and ribosomal RNA, seen in the far right panel, is another form of RNA. So there's nothing mystical here. Messenger RNA is only the information that goes from DNA in the nucleus out into the cytoplasm, gets loaded on the ribosomes, and directs the translation of protein. Next slide. Now, what is being translated in the case of these vaccines? All of the genetic vaccines, which is to say all three that are licensed here in the United States, are genetic vaccines. 2 of them involve mRNA. 1 of them involves an adenovirus vector. That's called J&J. Okay? So all of them are expressing the spike protein. The spike protein is the orange motifs in this schematic of a coronavirus. And you can see here we've got some general diagrammatic orientation in terms of the envelope protein and the membrane protein and the nucleocapsid protein and the RNA, etc. But the business thing for all of these vaccines is the spike protein. The spike protein has been modified with a 2 amino acid substitution in the receptor binding domain. That's the little tiny tag that's sticking out there at the top. Okay, so that's what we're talking about, is the main antigen here is they're using the entire spike protein, but in fact the main business part that elicits potentially protective immunity to the extent that it does is the receptor binding domain. We're going to go a little deeper into that in a minute. Next slide. Next slide. There we go. Okay, so now we're going a little bit deeper, and this will help answer a lot of the questions about what is actually in these RNA vaccines and what are they there for. Okay, so stay with me. You see these little complexes. I wish I had a laser pointer, but we don't. In the upper left-hand corner of the upper panel, you can see a very crude schematic, and you can see the various components. Now, I can't say anything about whether there are additional components in the formulation. That's a whole nother issue, but right now let's just focus on the core ones. When I speak in my podcast about fats, what I'm talking about is the helper phospholipid, the cholesterol component, and the ionizable lipid. The helper phospholipid helps facilitate cell fusion. These are highly fusogenic lipids, like diallyl phosphatidylethanolamine. The ionizable lipid in my original work was what's called a quaternary amine. And so it is locked into always being positive. The big discovery that was made that makes this really supercharged in animals and humans is movement from a quaternary amine that's always positive to a tertiary amine that is only positive at certain pHs. And what that does is make it so that these assemblies, this is self-assembling particles, the nanoparticles that you hear about, are formed in a spontaneous association. RNA is negative, and these lipids are positive. So just like a battery, like iron filings, negative attracts positive. Okay, these are electrostatic interactions, and they self-assemble. So the lipid that's responsible for collapsing the RNA and entrapping it are these things on the upper right. Those are structures for any of you who are chemists or biochemists. And the two on the lower right, you'll notice, are both tertiary amines. You see there's 3 carbon atoms attached to the nitrogen in those 2, acuitas A9 and mrna L5. So that's the business end of what collapses the RNA, is those lipids that are synthetic. Those are the ones that accumulate in the ovary. Those are the ones that we really don't have toxicology about, and that's the honest truth. So we really don't know about the reprotox associated with those lipids. When you hear about the ovarian data from Pfizer, from the Japanese disclosure, what it is talking about is the accumulation of those lipids in the ovary, not the spike protein. Okay? So it's good to have, make sure we get things right. Now, going to the left again, the additional components, the cholesterol and the phospholipid, helper phospholipid, increase the fluidity of this outer lamina of lipids and make it easier for it to fuse with cells when it attaches to those cells. It attaches to cells, again, largely through ionic interactions. Now, a lot of people have talked about the polyethylene glycol. That's abbreviated here as lipid-PEG. Okay, and for the chemists, this is polyethylene glycol with a short acyl side chain. The lipid PEG is used in the formulation, and you can see this schematically in the bottom 2 panels. The polyethylene glycol with the short acyl side chain that causes it to insert into this lipid membrane complex is there to keep these things from aggregating. One of the big problems with this cationic lipid RNA or DNA formulation technology is that it will aggregate. It will form flocculent material, and you'll see it if you leave out these vials too long at room temperature. You'll see them start turning kind of pearly white. And what that means is they are aggregating to large enough particle sizes that it's diffracting light. That's what you're seeing when you see it start to become a little more opalescent. Okay? This is a main problem with the technology. Usually you have to formulate and then use it right away, otherwise it'll flocculate. And so it was discovered that if you add polyethylene glycol, now we've lost our slide again. If you add the polyethylene glycol, like in the left lower is the growth schematic, that helps keeps these things from aggregating. The reason it has a short acyl side chain on the polyethylene glycol is so the PEG falls off when it gets into your body. This is only meant to stabilize the lipid formulations in the tube, in the vial, before injection. So it falls off, and if you have patients who are hypersensitive to polyethylene glycol, that can put them into anaphylactic shock. So a lot of the short-term anaphylactic shock that is being observed is, when it's observed, it may be due to psychosomatic problems. Some people just faint when they get a shot, but to the extent that it's triggered by a molecule, it appears that is due to the polyethylene glycol falling off. For example, when I received my 2 shots of Moderna, I could feel, my first ones were in my left arm, my first one. And within about half an hour, I could feel a sensation down at the tips of my fingers. That was not from protein expression. That was from the polyethylene glycol. and perhaps from the nanoparticles. Okay, so that's what's driving that anaphylaxis, is people that are reactive to polyethylene glycol. Now remember, forgive me, this is for CME credit, so I'm talking a little deeper than I usually do. So now you have a sense of what are the components, and you can see it very nicely that the schematic on the right lower is more accurate. You actually have small bubbles of fat entrapping RNA, and there's the structure of the RNA. We don't need to go into that. And those are surrounded by more fats. Those fats are helper phospholipids, cholesterol, and the ionizable cationic lipid that's proprietary. And then they are typically have a shell of additional fats around them and polyethylene glycol inserted into that so that the particles are stable in the vial before you inject them. Next slide. So my goal after this, while they're loading up the next slide, is that at the end of this, you guys are experts on how this technology works. You can talk to your patients, any questions, you can answer those. You don't have to say, I don't really know. Okay? That's the goal. Now, the thinking was that there are many different cationic lipids and tertiary amine cationic lipids that are being used in vivo, and subtle changes seem to change where they go in the body in animal experiments. Remember, we've never had large-scale human deployment of this kind of technology in the past. So just because something seems to happen a certain way in an animal doesn't necessarily mean that's the way it's going to happen in humans. Those of us that do this kind of research, we always say, mice lie, monkeys mislead, and the only thing that proves activity in humans is activity in humans. Okay, that's the truth of it. Okay, so the theory was that the specific lipids that are being used target the lymph nodes. Those formulations are supposed to go straight from the deltoid where they're injected into the draining lymphatics and track to the draining lymph nodes. Now what we know is that's not true. That was a nice theory. That may be the case with a large fraction of the lipids, but we know from what's been disclosed and received under Freedom of Information Act is that we know, and we know that the pharmaceutical companies know, that these things don't just go to the lymph node, they go all over your body. That's another thing, okay? But this was the theory of how this was supposed to work back in the day, like, you know, seems forever ago. Okay, next slide. So now we're starting to put together the whole picture. So now I'm going to start talking a little bit about immunology. In the upper left, we have a schematic of a lipid RNA complex. And that schematic is actually a little bit wrong because at this point, the polyethylene glycol should have mostly fallen off. That attaches to cell membranes through largely electrostatic interactions. It's not receptor mediated. It directly fuses with the cytoplasmic membrane, and pH changes trigger release of the RNA as a free molecule. That RNA then traffics in the cytoplasm to the ribosomes. That probably is a tubulin-dependent process. It loads onto ribosomes and gets repeatedly translated, so you end up with polyribosomes producing multiple polypeptides that are encoding the spike protein. This is probably happening on the surface of the endoplasmic reticulum. The spike protein enters the lumen of the ER, is processed through the Golgi, and then displayed. It gets displayed in two forms. It gets displayed as intact protein, that's shown on the right, which then can interact with B cells, as well as T helper cells. And on the left, it gets loaded onto MHC1 and MHC2 molecules that are involved in education of T lymphocytes. The T lymphocytes then interact with B lymphocytes. Okay, so that's the logic of the mechanism of action, is that you end up with intact spike protein as well as spike protein fragments that are presented to T cells, okay? So we know from the literature that intact protein gets cleaved off and some fraction of it circulates. We don't know, for some reason no one has done the experiments. We know that those free spike protein subunits, as when they are native spike protein as produced from the virus, are toxic. They have a large range of toxicities. ACE2, which they bind to, is a super important regulatory protein in human biology and homeostasis. We know that they are associated with opening the blood-brain barrier. We know from multiple studies that they're directly cytotoxic. I'm sure there's many other activities associated with spike that are unknown. The native spike also manipulates the NF-kappa B pathway and upregulates COX-2, the pro-inflammatory protein that produces prostaglandins, etc. Okay, so this sets off, spike is involved in setting off the whole inflammatory cascade, but it does a lot more. But when we see the amount that is produced in that Harvard and Brigham women's nurses study, when you calculate those levels, to my eye, as a gene therapy specialist who was involved in development of this technology, I was blown away. I never anticipated any system that would produce this level of protein using non-viral delivery. This is truly a big hammer in the gene therapy world. It is an amazing amount of protein, but like I like to say, you give a 3-year-old a hammer, everything becomes a nail. The problem, I don't think, is the technology, the problem is the payload, it's what's being expressed. And they went forward with intact spike protein. And they didn't realize at the time they did it that the intact spike protein had these biologic activities and toxicities. So there we go. Now that was the start of the immunology. We're going to go a little deeper in the next slide. Again, forgive me, it's for CME. Next slide. Okay, so here's the summary of what's happening immunologically. We're having these complexes, they're getting into cells, they're being translated, they're presented on the surface in both MHC class 1 and class 2 molecules for T cell activation and interaction, and they're also presented as holoprotein, which is useful in B cell activation. Now this is really important, this next part. Notice in the upper right, memory T and B cells. Okay, you not only get activation of effector cells that expand, these are the ones, plasma cells, etc., that produce all the antibody. These are cytotoxic T lymphocytes, these are effector cells. But you also generate memory B and T cells. What seems to be happening, in my opinion, with the short-lived activity of these vaccines, the reason why we're seeing such an abbreviated period of effectiveness, okay, durability is the technical term. The reason why we're seeing such short durability is because these memory B and T populations are declining rapidly. That's paradoxical. That doesn't normally happen. Now I'm going to talk in a minute why it may be happening. I'm just going to surf over it really brief, or we're going to be here for half an hour. Okay, so memory T and B populations are super important for durability, and for some reason they seem to be dropping off rapidly. Then we have the production of the neutralizing antibodies, and we'll talk about that in a minute. So if we can go to the next slide. Now, this is my brief one slide on the J&J vaccine. So now you understand all that stuff about the molecular biology and the immunology of the virus and the antigen and how it's being presented and what it's doing. It's all the same stuff with J&J. The difference is that the adenovirus vectors, and these are viruses, that have DNA inside the virus, and that DNA is recombinant so that it will produce the spike protein. It includes the spike protein gene, which also has this 2 amino acid modification, just the same as the RNA does. From the antigen point of view, it's all the same stuff. But the key difference here is we're using a virus that injects its DNA, which goes to the nucleus of your patients, And these are designed for long-term, high-level expression of protein. These are explicitly gene therapy vectors applied to vaccines. There's a whole history there. So when we think about these two things, some people say, oh, adenovirus J&J, that's a traditional vaccine. False. Okay, that is not true. This is not a traditional vaccine. There have been more vaccines tested with adenovirus than with RNA, but this is absolutely not a well-proven technology. This is the first time that that technology has been widely deployed in humans. It's been deployed at smaller levels, and there have been other adenoviral vectored vaccines licensed. And by the way, they don't have this spectrum of adverse events. They don't cause clotting. So therefore, it's not the vector, it's the thing being expressed. It's the spike. I'm sorry, Reuters, that's just the way it is. Okay? There's this thing called science. Next slide. Next slide, please. Okay, now we go a little bit deeper. This is super important to understand for your patients as you're trying to understand what in the heck is going on. Why do some patients get better protection than other patients? In addition to the decline of the memory cells, there's other factors. So there's been an amazing international collaboration led by the La Jolla Institute of Immunology that has carefully mapped the different targets on spike that effective antibodies can bind to. And that's a whole hour-long talk about how that happened. But I wanted you to have in your mind, in that upper middle panel, that is the size difference between spike and a single antibody. So have that in your mind, okay? Sometimes we think about antibodies as little tiny things and spike is a great big thing and there's a bunch of antibodies binding to spike. False, okay? That's the true size difference in that model right there between spike on the left and the antibody that's binding to the receptor binding domain on the right. Now, let's look a little bit at that receptor binding domain. Remember that? That's that little tag that's sticking up at the top of spike that I showed you in one of those early slides, that little tiny bit that's sticking up there. That's the thing that allows spike to bind to ACE2 on your cells. It's just that little tiny tag. And then what happens with spike, just to say it, is spike is like a syringe. Once that thing gets engaged, there's a series of changes in the structure of the spike protein that results literally in the injection of the RNA from the virus into your cells. That's how that works. Okay, so that's what spike is a molecular syringe used by the virus to inject its RNA into your cells. And the thing that triggers it is that little tag in the upper right that's got all the colors on it. What are those colors? Those are the known effective antibody binding sites to effectively block spike activity. Now, what has been brilliantly demonstrated by the La Jolla team is that we generate a whole lot of antibodies. And some of those, and by the way, the monoclonal antibody people have generated a whole lot of antibodies. Those antibodies often interfere. You can't assume that 1 + 1 = 2. With antibody inactivation and neutralization, if you have two antibodies that are binding next in adjacent sites, they can actually interfere with each other and make sure and result in inactivity. Now, when your patient gets the vaccine, they're producing a polyclonal antibody response, and those antibodies are all competing and interacting. And many of those interactions are destructive. They are not constructive. There are some sites that if you combine an antibody with one of those on the receptor binding domain, and for instance, one that binds to that little blue spot, that are highly cooperatively antagonistic. So when those two antibodies bind, you can get much more activity than if you just have one, which is why the antibody cocktails work. And you will see over time, here's good news for you, I'm sure there will be more and more potent antibody cocktails coming out now that we understand about these interactions. Now, on the left, we've got a little more detail. These are structural mapping of the spike protein. And one of the things that's important about the receptor binding domain is that it flip-flops, okay? Which means that it's constantly moving about in space. And so antibodies that work against one part may not work against another part. And in the vaccine, we lock the spike into a certain conformation, but that's not how it exists on the virus. In the virus, it's moving around in space all over the place. Why is that important? It has to do with natural immunity. That's what I'm setting up. The whole thrust of this talk is taking you to a place that you can better understand why natural immunity is better than vaccine-induced immunity. That's the reason why what I'm sharing. Now, in this odd one, that's in the middle lower, you're looking straight down the barrel of the gun. Okay? See those three things that are hanging out on the outside? Those are the receptor binding domains, because spike exists as a trimer, and it forms a channel. And now you guys all know why. Because that channel is the interior of the needle of the spike syringe through which the RNA from the virus gets injected into your cells. So hopefully now you've got it in your mind about kind of the size relationships of these things, some of the interactions, and how spike works and why it works. Next slide. Okay, so I'm going to take you even deeper. Again, forgive me, this is for CME. I'm talking to the physicians here. T-cell immunity. Now, here's some super important things to understand. You know, this is an obscure journal, probably hardly peer-reviewed. It's called Cell. This came out quite a while ago. What you're looking at is a graphical summary of the results of some sophisticated immunology, but that we don't need to go into that level of the science. What has been clearly shown in the lower panel in the unexposed patient is we have all been experiencing common cold coronaviruses our whole life. Those common cold coronaviruses elicit cross-reactive helper T cells and effector T cells, okay, so 4s and 8s, against spike epitopes, non-structural protein epitopes, and M protein epitopes. So you already have immunity against cross-reactive T cell epitopes. All of you do, whether or not you've had SARS-CoV-2. But it's a limited repertoire. It's only those things that cross-react between common cold coronavirus and SARS. But it's the reason why the amazing thing that's seen in the literature again and again is people that get infected, they raise neutralizing antibodies and effector T cells within high titers within 2 weeks, because those are recall responses, okay? Recall immune responses. They're not primary immune responses, like you've never seen those things before. You've already seen them. So your memory B cells and T cells are expanding and responding, okay? Now this is if this is advanced reading, go look it up yourself. This underlies the problem of original antigenic sin, which is probably the other thing that's driving the short-lived nature of the durability of these vaccines. It's just the hard truth of it, okay? Your body will continue to react in part by amplifying the CD4 and CD8s that have been generated by your common cold coronavirus exposure previously, which are not particularly effective against SARS-CoV-2, but they're there. Now, the upper panel shows that in the natural infection, you're generating both CD4 and CD8, so effector and helper cells that are reactive to spike, M, nucleocapsid, and the non-structural proteins, okay? And of course, the CD4 helpers are interacting with your B cells to generate your IgA and IgG, and you notice with natural infection, you're getting about 80% IgA and 100% IgG in terms of patient responses. IgA is the one that becomes dimerized and is expressed in your nose and your saliva and is neutralizing the antibody when it first hits your oral mucosa and your nasopharyngeal mucosa. So sorry about the high-end immunology stuff, but but that's what we're here for. So let's see, measuring immunity is key, and it's key for understanding your status after you've been infected and for being able to document that the mandated jabs for people that have natural immunity don't need to be there, okay? In the best of all possible worlds, the government would say, oh, if you had a test showing strong antibody titers and T-cell responses, you're good to go. That would be a rational public policy, in my opinion, okay? But what's super important that we all remember is that in the unexposed, we're not truly unexposed. We've all been subjected to common cold coronaviruses and they cross-react. Next slide. Okay, now we're finally winding down. This is getting more and more focused on natural versus vaccine-induced immunity. In the natural immunity, here's a structural map of the genome of SARS-CoV-2. You'll notice that there are a small number of structural proteins, 4, and then a whole bunch of non-structural proteins, which the virus uses to enable its own replication, manipulate your or your patient's immune responses. So these viruses are really good at tweaking immunity to their advantage. And it's these non-structural proteins that do that. But you're raising particularly T-cell responses against all those proteins when you generate natural immunity, when you are recovered. As opposed to the vaccine immunity, you're eliciting immune responses against a single protein spike. That single protein in itself is associated with toxicity in the wild type, and it appears also in the vaccine expressed. But you can appreciate the difference. As the virus evolves to escape the single antigen spike, am I cutting out? No, I'm still here. The virus is evolving to escape spike, and in the vaccinated, there's no other backup immunity other than their prior exposure to natural circulating cold coronaviruses. In natural immunity, you're having immune responses against many, many proteins, non-structural, structural, and accessory. Huge difference. Huge difference in terms of selecting viral escape mutants. Okay, this is why my good friend Gert van den Bosch keeps trying to alert the world in his own kludgy, sciencey way that this is a bad idea for universal vaccination, because what we're going to do is drive everybody towards primarily having an immune response against spike. And once we generate escape mutants from spike, it's just going to blow right through us again, yet again. Next wave. Okay, natural immunity is better. Fundamentally, whatever Rachel Walensky may say, it is fundamentally superior, just from first principles. Next slide. Now this is the last of Eat Your Vegetables slides. Next slide, please. Okay, but I think is one of the most important. And I encourage all of you to look up this very nice BMJ article. This is just one key point, a couple key points that I wanted to highlight for you. Okay? As we know, there are multiple studies, over 100, that demonstrate that natural immunity is superior both in breadth, in durability, and effectiveness in protecting against disease and death. Full stop. Okay? Whatever the CDC happens to say in that cooked up, contrived study, and if you haven't looked at the Brownstone Institute's analysis of that study in comparison to some of the other studies, I recommend that you do. Okay? The study that the CDC put out is highly flawed and not peer-reviewed. And there's over 100 other studies that refute it, even though the press has latched onto it and they're pushing it into everybody's mind. That's propaganda. I don't know how I could say stronger language, but it is not a valid study. Multiple studies, and here I give you some examples, have demonstrated that people with a history of SARS-CoV-2 infection experience greater rates of side effect after vaccination. This is super important for your patients. And I can tell you from first-person experience. I was infected in February of 2020. I took the Moderna jabs because I wanted to travel and I thought it would help me with my long COVID. What I had was severe adverse reactions. My systolic went up to 230. Okay, I developed restless leg syndrome. The good news is I've survived the stress test and I didn't blow out either my aorta or vessels in my brain, but your older patients may not be so fortunate. Okay, the data are quite clear. Vaccinating after natural immunity has been generated yields many more side effects, the prevalence and the severity, than vaccinating the naive individual. Do not vaccinate the previously infected, full stop. You're putting them at higher risk. Now, I want to share a little insight that I hadn't thought of from Patrick Whalen of UCLA. Basically, in this last bullet point, what he's warning about is the development of circulating immune complexes. And I think he's got a point. I think that there's a reasonable chance that when you have natural immunity, you have high levels of circulating antibodies, and then as Dr. Jill Glasspool Malone first taught me, what happens with the vaccination is you're loading your patients with a bolus of protein. It's not the same as a viral infection. With a viral infection, you're getting a gradual increase of these proteins in your body, in your patient's bodies. With the vaccine, you're giving a bolus, and it is a whopping good amount of protein that's being expressed. And it's being cleaved off of the surface, and it's going into the circulation, and it's encountering circulating antibodies. And what happens when you do that? You form immune complexes. What do immune complexes do? All kinds of stuff, that arthralgia, joint problems, muscle problems, cardiovascular problems, kidney problems, lung problems, et cetera, et cetera, et cetera. You know, your physicians, immune complex disease equals bad. And I think Jill has got it right. The vaccination is not the same as natural infection in terms of the kinetics of protein expression. And when you give a bolus of protein into somebody's body, when they already have higher levels of circulating antibodies, you will be generating immune complexes. I think Dr. Whalen is correct on this. Okay? So again, don't do it. Now, take away 3 key points. Okay? 3 key points. Get this in your brain, share it in social media, get it out to your peers. There is no reason to vaccinate children. They don't have a risk of disease. Number 2, natural immunity is superior to vaccine-induced immunity, full stop. And don't vaccinate those that have natural immunity. Number 3, don't interfere with physicians that are providing life-saving medications to their patients. Stop it.